Hi, this is a continuation for the power electronics lectures. And in the previous lecture, we have covered the linear operation and switch operation of some circuits. And maybe we have just gone through some circuits like this circuit. And the objective was we have a 100 voltage source that I can't change, but I want to deliver 50 volt to my load. And my load was just a resistive load. Okay, it can be machine or a heater or any other things. And I use the transistor just to make the control and achieve my 50 volts here. Okay, and there are two ways to make this objective achieved, which is by linear operation, supplying continuous current to the base and making the transistor in the linear mode, or I can saturate it and cut it off, okay, by applying a switch signal on the base here and make the average voltage on the across the load to be as well 50 volt. So remember here, we have the objective to be achieved, which is 50 volt across my load. And two ways here, okay, and we discovered that the first way, which is linear mode, has about 500 watt dissipation, okay. The second way is ideal is zero dissipation, 0 watt dissipation, but we have practically some dissipation, okay. So today I'm going to continue this, but I will show you how I use LTSpice to approve or validate what we have already covered here, okay. So I will build this circuit with 100 volt source and resistor and also transistor, and will supply two different signals here. One signal is continuous signal and the other signal is pulsating signal, and each of them should achieve for me the 50 volt across my load. I will use LTSpice as well to calculate for me the power dissipation across or by this transistor, and also the total efficiency for the circuit. I hope you will find it interesting, but remember, this video is not a tutorial about how to use LTSpice, because I'm going to show you a circuit that already established. Already I have done it before. Already you will find all the details already made before, so don't worry about this. You will learn this by step in the laboratory sessions. So I will just show you a demo how to use LTSpice and the ability for that, just to approve what we already covered. So let's now start using LTSpice for the purpose of linear mode and switch mode comparison. Don't be afraid of all of these details. You will be covering some tutorials and also tasks how to do this simulation later in the lab. Okay, so for the instruction or codes on the right here, we will use them just to calculate for us the efficiency and average voltages and powers across all the components here. So don't worry about how we write this. I will give you the easy way to write this later and make LTSpice very efficient tool to calculate for you everything. And we have this circuit here as we show in the slide. We have 100 volt source, and that will supply a load which is 5 ohm resistance here. It might be a motor or heater, but it has the same resistance. And also we use the transistor, okay, to calculate or just to generate the average voltage here to be as we want. Now we have two sources here that will be injecting some signal to the base of the transistor. One of them is the linear source. I call it the linear because it supplies just continuous supply of 2.33 volt. Why I choose this one? Because according to my trials, this is the value with this resistance that supply the I base that really makes the voltage across the transistor 50 volt. So this voltage here, okay, sets IB to be here 50 volt. It's not just something I just want to make up because of the simulation. No, if you try it, you will not get 50 volt here if this value is not 2.33, okay. So we will get 50 volts here, and we will get another 50 volt there by this value, and this will be supplied continuously. That means we are in the linear mode, okay. The other source is a switch mode, which is just source with pulsating signal, and that's it's a signal of 10 kilohertz with 50% duty cycle. Okay, so I think you are aware now about these things. What I'm going to do, I'm going just to connect the linear source first to the transistor, okay, and I will run the simulation. The simulation will run and show the transient response, okay, it's called the transient simulation, and will show the signals versus time, okay, and then we can calculate the average voltage and power. Okay, so let's now run it, and I will run it from this icon here, okay, and after that it runs now. I can see the voltage across the resistor. I can just zoom, okay. I can measure the voltage across the resistor, okay, by pressing here and then go shift it to this point, and I can see the voltage now across the resistor, which is about 50 volt exactly, okay. So we have reached our objective, which is 50 volt across our resistor, and definitely the voltage between this point and the ground, okay, will be another 50 volt, or 49.86, which is about 50 volt. Okay, you can adjust this value now by readjusting the 2.33 voltage. Okay, so we have now got the 50 volt, but what about the power dissipated by the transistor, for example? So I will just click on the transistor, but before clicking you have to just click or press the Alt button, okay, on the keyboard, and you will see here something like thermometer. Okay, this thermometer reflects there is temperature, okay, and that temperature come out from dissipated power. Okay, so I will just click on this and see how much dissipated power here. It tells me that, look at that, once I press Alt and click here, okay, the LTSpice had generated for me an equation. Look at this equation. This equation represents the dissipated power, and I can take that equation and calculate the average and do other things. Now, it's red color here. That means, and here's the scale. Look at that, 500 watt as we expected. Okay, so the dissipation in the linear mode or linear operation for the transistor in this circuit, 500 watt. Okay, what about the efficiency? To calculate the efficiency, I have to use some extra codes. You will know how to use these and how to measure it. Okay, and I'm asking it to measure, for the first time I'm asking it to measure the average voltage across the resistance here. Okay, and look at that, I'm asking dot measure V output average. I give it this name, and then I use the command AVG, which is average of what? Of voltage between this node and this node. What are these nodes? I took it from here, okay, because this LTSpice give it to me that this is the voltage across the load. I can give it a name for N001. I can give it another name by renaming every wire. Okay, so the first line is asking to calculate the average voltage. The second one is asking for calculating the average power input, okay, which is from the source. Okay, so I have done the average average power equation using LTSpice by clicking the Alt button, and then by looking at the thermometer here, and by pressing it, it gives me another equation. I just put it here, okay, and because the current is opposite, so I have to just to add minus here. The power output, okay, across the resistor, okay, and also which is voltage times the current, okay, and also the power of the transistor, which taken from that equation here, okay, the average of all that given by LTSpice, so I don't need actually to write it from my own, okay. And the last command is to measure the efficiency or calculate the efficiency, which is 100% times the power output, which is the coming to the my load, okay, divided by power input supplied by my source. Okay, and then after simulating, okay, I can go to where I find these results. I can go to view and then go to spice error log. This is the file, okay, where we find our results. I'm not sure I call it error log, but this is the way here. Okay, so if we just gone through this file, you don't need to go for all details. Just go to these details here. Okay, it says the voltage average, okay, because this is the last one we have added in my file. So voltage average here is 50 volt. Okay, thumbs up, we got it. Okay, for the power input, it says here we have 1002 watt as power input from the battery, but how much power output reached my load is the power output here, which is 500. And how much power dissipated in the transistor, so it will be separated, power transistor dissipated, it will be another 500. So we have 1000 watt it absorbed from my battery, my source, and half of it dissipated by the transistor and half of it dissipated by my load. Okay, this is the problem. Dissipation of the transistor is very high, and what you expect about the efficiency? Yes, it's 50%, because 50% of the power dissipated by the transistor, 50% dissipated by my load. So the efficiency is 50%. Okay, so this is how we use the LTSpice to do that. Now let's go to the, I will teach you later how to make all these simulations. Now let's go to the second part. I will delete this wire now and replace it with a wire from my pulsating source. Okay, 10 kilohertz, 50% duty cycle. Run it, the simulation again. We will get these signals here. Okay, but don't worry about it. Okay, we will go to view error log. Okay, and we will see the results here. The output average voltage again is about 50 volt. Again, we achieved that. The load is happy now and getting the 50 volt. Let's go to the power input. Power input now is giving us about 1000 watt. It's similar to the first scenario. The power output delivered to the load, it was 500, and now it's about 990. Okay, 990 watt. So it's very close to the 1000. Okay, and the power dissipated in my transistor about 9.8 watt. Look at the big difference. The dissipation in the transistor for the first case in the linear operation, it was 500 watt, and now it's about 10 watt. Look at the big difference here. And when you think about this, you will rethink about, do I need a heat sink? Do I need a fan? Do I need multiple parallel transistors to just dissipate all that heat? But now I think it's easy to be done. All right. What about efficiency? 99.1%, and this is very expected. That's why we use the switch operation, because we achieve a way higher efficiency, and also we can use our transistors without lots of stress in terms of heat and power dissipation. I'm also interested to show you the efficiency versus the duty cycle. So to do that, I will change here the duty cycle. The duty cycle here is the 50 micro, which is the turn on time. I will give it a name like duty. Okay, duty C, just to make it different from any other parameter in the software. Okay, so this one I will write now a new command, and that command will take the duty cycle and shift it from value to another value, okay, over a range, and we calculate the efficiencies for all that. So let's now write the command, which is .step. Okay, I will step now the duty cycle, okay, from, for example, 10% to 90%. Okay, let's make that, okay, just to avoid the 100% and 0%. Just I want to make it in the middle. 10%, 90%, and jump every 10%. Okay, so every 10% you make a jump and give me about 8 or 9 results. But here I forgot something, which is I have to tell the LTSpice that UTC is parameter, okay, because I haven't used it before, this parameter, so I have to declare its parameter. Okay, so this is how we really shift the duty cycle from 10 to 90, and every step is 10%. And also I can't write 10 and 90 and 10 like that. I have to give it, because it's turn on time, I have to give it a unit like micro, because it was in microsecond. Okay, so now the simulation will take the 10 micro, okay, which represent the 10% duty cycle, and run the simulation and generate for me all the efficiency results, and then we'll step to 20% or 20 micro and 30 micro, and every time we got the efficiency, and will produce for me a table for that. So let's now try to run it. Now it will generate many curves on top of each other. Okay, and you can see here the run. Look at that, there is run 3 out of 9, so we have 9 runs in this steps. Okay, and now it's now bringing it to finish, 7 out of 9 and 8 out of 9 and then 9 out of 9. It's finished now. Okay, sometimes take longer, but yeah, we finish it, and we go to log. What in the log? Here we will see table, and that table for every step. Okay, and what are the measurement for each of them. Okay, so for 10% to 90% here, and here's the steps for 1 2 3 until 9. Okay, and we have the average power input and average power output. So look at the average power input for all the duty cycle ranges. We have about 200 here and about 1790 watt. Okay, and but I'm not interested in power input and power output and power dissipation now. Look at power dissipation, it looks also good, because from 10 to 90 the maximum dissipation here I'm getting about 16 watt, which is really good. Okay, now go to the efficiency, look at this table. Okay, 98%, 98.4%, and then 99.18%. So it's very high, over the 98.4% all the time. Okay, which is very high. So for the average voltage, look at that. When we set the 10% duty cycle, we got average voltage 10 volt, 20% 20 volt, 30% 30 volt, 40% 40 volt, until 90% about 90 volt. It looks very, very nice. Okay, now the efficiency here are very promising, that for all my range I'm getting efficiency over 98%. And you can also draw this by clicking on the efficiency by the right button, mouse button, and go to the plot.step measurement data, and just it will bring a new window. And once you just add a trace that you want the efficiency, okay, look there. Okay, look, it's very nice one. It shows from 10 duty cycle to 90 duty cycle what will happen to the efficiency. It starts from 98.4% to 99.1%. Okay, so you can really use this one for also the maybe I forgot also to draw the output voltage. Okay, average voltage, and that should be a linear one. Output voltage average. Yes, so we have the duty cycle and the output average voltage. They are in linear relation between each other. So we have 10% here, it gives me 10 watt, 10 volt. 90%, it gives me 90 volt. I hope you found it interesting how to use the LTSpice to just approve what we already generated in theoretical lectures, and also how to generate these calculations and also these tables that maybe some other non-free softwares can not easily can generate these results for us. I hope you are now motivated about how to use LTSpice, and maybe you will try to download the software and be prepared for the next lab, okay, where I will explain for you the how to use LTSpice and some tutorials step by step, and see how we can generate a file like this one. I will share with you this file, okay? Just if you are interested, you can run it by your own and see if you can get similar results.